And all right, this is our second implementation week, but I think at this point we've pretty much finished everything. So first of all, let me show you the results of investigating into the original TD3 implementation and how it produced, what kind of results it produces. So that should be just the cleanurl.sh. I just did a redirect. Let me close down irrelevant environments. So I have to investigate into this, but for whatever reason, cart poll is not executed until 2 million time steps. Oh, I see. Because of the total time step that I gave was 200,000. But yeah, that's fine. Okay, let's see. So first of all, in mountain car continuous domain, do I have a video? Oh, so it actually doesn't solve the continuous. Really? So it doesn't get any negative reward, but it also doesn't appear to solve the environment. Is it? Let me double check. Yeah. Okay. So this is an interesting instance. So the mountain car continuous domain, the car just kind of stay in its original position, but somehow its episode rewards is -1. Really? I don't know. Something feels a little off here, but I'll look in.
Interrupt.
Yeah, go ahead.
I noticed the same phenomenon happening with a soft actor critic on Mountain Car Continuous.
So we don't have any algorithm that solves mountain car continuous, right?
I think the simpler one managed to solve it. Which one is it? Maybe DDPG? Maybe.
Well, I have all of the agents visualized here. None of them seem to make significant progress.
Yes, I think I was confusing with the DQN and the
Yes. The discrete mountain car DQN indeed solve it, so that's not a problem. But at least for the continuous action space, this seems to be a much harder problem. All right. Yeah, but anyway, let's skip into other domains. So something that TD3 achieves the state-of-the-art results. By the way, the scale also looks a little different. Some of the agent might be running in environments with limited time steps. So I think some of them, I actually set it up I actually set it up an episode length, so they're not running the full length of the game. But 1,000 should be the default one. In a more recent version of the algorithm, what I did was to basically don't set any episode length and just kind of use the default time limit length that are set by the author of those libraries, such as PY Bullet. But in any case, you can see that TD3 significantly performs well above others in the Walker domain. And I believe this is one of the visualization of the agent walking. And it's much better than a lot of the visualizations we see here, which appears to be not doing anything interesting. Right. Yeah, a lot of the algorithm seems to be stuck with this local minimum where the agent just kind of bend the knee and then not really doing any walking. And this is even a funnier example that it just does this. What is this algorithm? Let me see. So this is DDPG. But as you can see for the reward, I'm pretty sure for Walker, the default time steps is the default episode length is 1,000. So the scale will be correct. And as you can see, TD3 achieves the state-of-the-art results over here. And let's take a look at humanoid. Similarly, TD3 also achieves the state of the art results. And I think it's not excellent. As you can see, the agent is kind of walking, but doing something really awkward, but it's able to walk without falling over and not doing something ridiculous like this, right? I always thought that this is pretty funny. Um, so that's for humanoid. And for Reacher, pretty much in all of the PY bullet environments, TD3 is able to reach state of the art. And I'll get into what kind of adjustments that I made compared to my first pass implementation of TD3. What changed? Because my first implementation of TD3 wasn't performing exactly very good, but we'll get into that. And pendulum, it's able to solve it once you swing up like here. So as you can see, once you swing up over here, it stabilizes. So that's very good. And in Hopper, it's also again state of the art. So I wonder if because SAC Soft Actor Critic was performing very well in this task, and I want to compare what they look like. Okay, so this is Software Actor Critic. Okay, hold on. Let's take a look. Can you guys see the little letters here? Hello?
Like barely.
Barely. Okay. Okay. In that case, I'll try to explain what they are. Um, okay, let me try this. So these two, the on the top left are TD3, and they're performing very well. And then on the right are also TD3, also performing very well. And then these four are DDPG. The second row is DDPG, and they're not performing very well. And after a few steps, it seemed to just kind of fall over. And then over here, these two are SAC. On the third row, the first two are SAC. And it's interesting because the second one seems to perform very well, but not the first one. But even that's the case, it seems TD3 is able to, the agent trained with TD3 is able to run much faster. So that's very interesting for me. Okay, but yeah, how to get out of this? Okay, looks like it just crashed. So that's for Hopper, which I believe TD3 still achieves the same state of the art results, and also it appears to be it appears to be not very sensitive towards different random seeds. And another thing that I'll point out is that I believe these PPL or DDPG they were run with the episode length set, but I believe the episode length should be the same, so there shouldn't be any discrepancies. Yeah, so I set the episode length to be 1,000, but I'm pretty sure that for Hopper or Bullet End, the default the time limit episode length is also 1,000. Lastly, inverted pendulum. I think in this environment, almost all algorithms perform reasonably well. TD3 also performs very well. So yeah, so that's basically for a review of all of the environments that TD3 has run, and it has received very good performance. And now let's get into what kind of changes I made such that these things happen. And I want to check something real quick, see if I can show you the performance of my implementation of TD3 initially. So I may have put them in this folder. Did I? Right. So this is, wait, is it? No. Okay, maybe this. Okay, never mind. So basically the story was that my initial implementation of TD3 wasn't performing very well, but it's visibly better than DDPG. I think I may have posted a screenshot in our chat. Okay, I couldn't find it. But yeah, so for example, for Hopper, let's say my initial implementation of TD3 will reach about 100 or so for its episode reward, and it's very volatile. Sometimes it goes to 2,000, sometimes it goes to 0. So I was very interested in learning what's the difference between my implementation and the original TD3 implementation, and a couple things stood out to me. So let me show you what's changed. And for our purposes, this is something very important. Perhaps it's this. Okay, I think it's this file. Okay, I'm pretty sure it's this file. So a couple things that's changed. So first of all, I lowered the learning rate. So these are the hyperparameters taken from the original implementation. So first of all, the learning rate is a little lower. It's about twice as low, but hopefully that shouldn't be the problem. But most importantly, one of the major discrepancy is the buffer size. So in my implementation, I set 10,000 for the buffer size, but for the author's implementation, I believe that's 1,000,000. So that's wait, what is 1e6? That's 1,000,000, right? So that's 100 times more than what I had. Yeah. So that's the first major discrepancy in terms of hyperparameters, is that the original author's implementation uses a significantly larger buffer size. And the other thing is when you do the training, this is another major discrepancy in the hyperparameters. The author uses a much larger batch size. In this case, the author uses 256. That's also about 8 or 7 times larger than mine. And also when does your learning starts? So I set it to 5,000, which means the agent will just sample random actions from the environment action space before the 5,000 time steps has passed. However, the author uses 25,000. So that's another.
I had some experiments with the starting step hyperparameter, but it does not seem to matter that much.
Okay, probably not. But I would say the buffer size and the batch size maybe are the most important thing. Because I remember once I change the buffer size, I can see a very drastic improvement in the performance.
But I am a little bit doubting you only change the buffer size and then maybe you also change something else
Probably.
again.
Yeah, I
Just
was.
the buffer size does not, especially in the beginning, it's not even full. So maybe 10,000. Okay, maybe in that case. But since old experience is overridden anyway, I would say the buffer size will not really matter.
Right. There's a guy who wrote this paper on the. Maybe this guy?
Yeah,
There's a
yeah,
guy.
I read this paper.
Go ahead.
Yeah, no, I think that yeah, it matters. It matters, and it should be larger. I think like 50,000 or something at minimum.
Yeah, there's a guy who wrote a paper. Yeah, a deeper look at experience replay. Richard Sutton's one of his students wrote up this paper where they basically did an experiments to test out the performance, the impacts of using different batch size, and this is the results. So using 100 gives you something like this, and then 1,000, then 1,000,000, which is what's used in our case, and then this is 100,000. 100,000 actually performs worse, and 10,000, which is my original parameter, performs similarly worse. So that's very interesting. So what the anyway? So for a quick TLDR for the paper, what this author proposed to do is instead of doing instead of just sample from the replay buffer at every time step, what you would do is you use the current observation as well as sample from the replay buffer, and that makes the replay buffer very resilient towards the size of the replay buffer. As you can see, use 100 or 1,000,000, it doesn't matter. But yeah, so that's just something that reminds me of this paper. But let's
Could you repeat that again, please? What did he do to the buffer?
right. So let me show you.
It just keeps all the experiences.
Yeah, right. So every time you store the transition into the replay buffer, right? So in the way how the author does it is they store the transition, that's the same, and then use a batch, that's the same. However, the author uses the batch as well as the transition that just happened. Versus in the original DQN, it just uses the batch and it doesn't use the transition that just happened. Does that make sense?
So just using one transition changes the result so much.
Yes. Well, it's not only just one transition, but it's a current transition.
Yes, the current transition, but at every update.
Yes, exactly. So, like, if you just say use the original DQN, there's a chance that the current transition, will unlikely to be sampled.
Yes.
Yeah, exactly. So, yeah, just one current transition. I really like this paper because it's an investigate into something that's kind of interesting, and it also has really good results. All right. So let's get back into the TD3 implementation. Some other discrepancies are the size of the hidden networks in the neural networks. So I use 120/84, and the author uses 256/256. Let me think if there's anything else. Yes. So here is another major discrepancy over here. So my original implementation just say I produce an action and then I plus its exploration noise. However, in the author's implementation, after you do that, you also should clip the actions based on the the low of the action space and the low and high boundaries of the action space. And you also would do that when you do the policy noise to do the updates. So my implementation, again, I clipped the policy noise, and then I just added to the actions. But when the author does it, it also clips it by using the low and high boundaries of the action space. I think this may have been a really big may have a really big impact on the performance as well. But yeah, so that's it.
I do not know about the clipping during the exploration, like line 250 or something, because even if you do not clip and the action value happens to exceed the higher limit, I think the environment automatically clips it to like the upper and lower bound.
True, but it's a way you learn, right?
Does it really change?
I don't know. I think it might, especially because, as we discussed last week, if we look into it.
No, this one is the target noise, but during the exploration itself, since there is no value estimation involved.
Actually, I don't know if the environment actually enforces the low or the high.
It doesn't. So it
exactly.
will fail.
Yeah, I think that's how you can get very bad reward is by violating the low and high.
And I was actually playing with the lunar lander, and I had to make the clipping to make it working.
Yeah, I had similar experience. The environment doesn't really enforces the low and high.
But question generally, because you were describing like these hyperparameters, right? But the hyperparameters always some kind of like environment specific, right? So so it really depends on the environment,
However, in this experiment, we just use the same hyperparameter for all of the environments, and it appears to achieve state-of-the-art performance, I guess.
For these particular environments?
For pretty much all of the pi-bullet environments we tested.
Yeah. No, just for example, I was testing the real TD3 implementation on the Nalander, and I realized that actually, like, increasing the learning rate will speed up the training.
Increasing what?
Increasing learning rate to 7, as you did.
Right, and that would break things?
No.
It's still very good?
It's much better than the lower one.
I see. Oh, right. By the way, yeah, I did run the experiments on Luna Lander, and I believe that's one of the environment that has not been showcased here. So let me go ahead and do that. So do I have Lunar Lander continuous? No, not really. However, oh, did I have half Chata here? No. Okay. Right. So another environment we can actually look at, which I haven't added here, is Hapchata, which also, again, TD3 achieves state-of-the-art performance in all of the other algorithms. Seems to be the only one that performs well. So this is DDPG. DDPG actually. Okay, that's interesting. Did you guys see the movement? So the second one on the second row is from DDPG, and do you see that? What is that?
That's kind of weird.
Yeah, I don't know. With this continuous domains, you always see this random movement.
Learning curve, what's that frequent sort of unlearning behavior?
I think that's just sometimes the I don't know. That seems to be something that happens with all algorithms. It's not only just with DDPG. It's all reinforcement learning algorithms. It seems that you always see sometimes you have this dip. Yeah, but I don't really know. Let's take a look exactly what's going on. And also, let me change something real quick. But actually, let me also change something real quick.
Looks like a black market crash.
So instead of saying bipedal walker, I want to say bipedal walker 3 as well. Right. So bipedal walker 3, TD3 also performs very well. And all the other algorithms just kind of perform very poorly. I also have to, someone please remind me to explain the difference between the TD3 continuous action 2 and TD3 continuous action. But yeah, half chatter performs well as well. And I think that's pretty much all of the environments that I tested. Right. Yep, that's it. That's it, folks. All right, any questions? Oh, right. I need to explain the difference between TD3 continuous and TD3 continuous action 2. So do you guys know, can you guys imagine how I get the initial pass? How I investigate into finding out what's different in terms of the parameters for everything. Okay, that might not be a good question, but basically, not only you do inspections, like you look at the original author's code and try to figure everything, but also what I do is I try to seed everything so that I make sure that for example, the learning start, right? The learning starts at 25,000 time steps. What I was doing is to make sure all of the actions generated and all of the environment episode rewards is the same up until 25,000. And then I run the TD3 optimization for one step. And then I basically check everything. I check the key value. I check the gradient. I check the weights to make sure the actor and the Q network are initialized with the same weights to make sure everything is the same. So that's how I figure most of the difference out. And one thing that was particularly frustrating to me was that once I basically reproduce a lot of things, and then there's one thing that is very different. It's the replay buffer. The original author uses a different replay buffer that uses NumPy to do the random seeding. And then if I use the replay buffer that we have, then the seed is going to be different. The batch that are being sampled is going to be different, and that causes issues for me to have an exact reproduction. And during my experiment with Hopper, it almost seems the replay buffer actually makes a difference in terms of the stability of the algorithm. Using the replay buffer from the original author seems to perform quite stably, and seems to perform more stable than using the replay buffer that we have. But that really shouldn't make any difference, but I wanted to make sure everything was correct. So what I did was to implement this TD3 continuous action 2 using the author's original replay buffer, and the TD3 continuous action just using our replay buffer. And there's something with the noise implementation as well. I'm pretty sure the noise implementation, these two are the same, but they use different libraries, and as a result, their C cannot be aligned. So basically, TD3 continuous action is doing whatever makes sense for us, and TD3 continuous action is trying to use as many components from the original authors as possible. And it seems in our experiments, the orange line and the blue line, they perform very similarly. So yeah, in fact, it almost seems that our implementation is There's no major discrepancies. All of them perform very well. With Walker, with Hopper, yeah, it's fairly similar. maybe minor differences, but for the most part, they're the same. So what I might end up doing is to delete TD3 continuous action 2 because there's no. I don't think it makes a lot of sense for us to have two different replay buffers. But yeah, that's about it. Any questions or comments?
Yes, one regarding not regarding this algorithm, but general regarding the TD error,
TDR?
TD loss.
Sure.
What is the intuition behind this, and yeah, how it can be beneficial to
Like what does TD error mean?
It's the TD is TD loss. TD loss.
TD loss is just a TD error. Do you know what TD error is?
Yes, and but the question is how it can help you in debugging. Why you want to like visualize this. How it can be beneficial for you for debugging for whatever purpose.
So, well, first thing that I would expect is that the the TD error wouldn't just blow up. Because you want to minimize the TD error. The temporal difference error really should be the same. And we can actually visualize what the TD error looks like, right? So for us, it's a TD loss, right? If we ignore the outliers and then try to smooth it as much as possible, we can see that, yeah, TD3 is very good, right? Its TD error is very low, while DDPG is very bad. It constantly blows up very high. So I think this is also kind of uh, I think this also kind of demonstrates the main thesis of the TD3 paper, right? It's about reducing the functional approximation error. Did I answer your question or not really?
Yeah, cool. Yeah, thanks.
Yeah.
Actually, could you check the hidden size of the DDPG?
Yeah, the DDPG is using the 128. It's the hidden size that we always use.
That might actually be one of the cause of the high value loss.
Maybe.
It might be.
Yeah, it might be. So I would say something would be interesting is to run the DDPG implementation again, and then in this time we basically just use the same hyperparameters that the TD3 is using. Use larger major. Most importantly, use larger batch size and use larger batch size. Use larger learning start steps, and then use the same neural network, kind of hidden network, and then use the same replay buffer size. And I wonder if that's going to make a difference or not. My first intuition is that it's probably going to perform better than what we have here, but probably no better than TD3.
I think I actually have those experiments.
Comparing different batch size, or what do you mean?
The same hidden size as the authors, as well as the other hyperparameters.
Okay, could you show us?
If I can find it. Oh, by the way, what was the learning rate again?
I think it's 7e. 3e minus 4.
Okay, in that case, I use the way bigger one, but
That's fine. That's fine.
it does not change that much the performance.
With the DDPG, so the hidden size
Yes.
doesn't matter, right? Yeah,
No.
Yeah, that's what I would expect, I guess. So yeah, I really don't think the network size would matter that much in a way. The thing that is more important really is how you structure the algorithm. If your algorithm that doesn't work, I would almost never suspect the network size is a problem.
Well, analysis is too small.
Beg your
The
pardon?
capacity of the network, like capacity of the network is too small for the problem. Then it might be, that might prohibit it, learning, right?
Yeah, but I guess I have never encountered that sort of situation. Um,
Yes,
and usually I'm pretty sure it's going to be large enough. Um, yeah, I just never had a problem. I never encountered a situation where the the smaller network couldn't solve. It's like someone if I feel like debugging with hidden size is almost like debugging with learning rates. Like you might get better performance, but if your algorithm doesn't work well, it's usually not the problem of the learning rates. At least not that much. It's usually something else.
yes, but the too high learning rate actually can prohibit testing as well, and then
Yeah, for
uh,
sure, it definitely can be.
yeah.
Um, all right. Any other question or comments?
Mm, it's very nice results generally, and
Yeah, I'm very happy. We finally have a state of the art library that work as intended.
yes, and it's kind of like simple algorithm at the
Yeah.
same time.
Yeah, it's very simple and very,
It's very
very, very intuitive. I think it's
Yeah,
very
it's very
nice.
intuitive and very powerful.
Easy to implement as well.
Yeah.
Yeah.
Regarding this paper you mentioned, the author, at the end of this paper, he suggests that generally his conclusion is that replay buffer are not the great solution, and we will, for sure, we will need to implement new solutions. I would not agree with this. I think that the replay buffer's got a great future, and it's very simple and powerful mechanism.
Yeah, yeah. People should use that technique in the paper I just posted in a Slack channel. Yeah, I think it's a really good paper, and its result is it's very obvious.
Yeah, yeah.
Also, just yeah, overall very good. What?
Long live the replay buffer.
Huh? Beg your pardon?
Long live the replay buffer.
Yeah,
Yeah, yeah.
exactly. Long live play buffer. Yeah,
Mm-hmm. Yeah.
One interesting idea would actually be, as Lucas said maybe 1 month ago, to extend it with some more sophisticated memory process. So it's not just old data, but kind of interconnected data.
Are you thinking about like a long short-term memory, or maybe something else that you're referring?
Well, term, the memory aspect is achieved in the network itself. But if, for example, the replay buffer could serve as an external kind of memory, independent of the network,
yeah,
Uh huh. Right, right.
it might actually be like a different neural network that is just encoding the observation and that kind of stuff. But in this case, again, it might just become another Q value.
Right, right. But yeah, that's very interesting. Very happy with the results, and I think we could we kind of finished all of the work for the uh, during basically the first 3 weeks, and we didn't even have to go to the fourth week. So for the next week, we can take a week off, or we can take a look at some other work. Is there anything that you guys are interested in studying?
I don't know. We mentioned something about this distributional uh,
Yes, yes.
learning,
Mm-hmm.
so
Yeah.
that's good. That looks good.
Yeah, recently I've been looking at this paper that I think might be very, very interesting as well. And since it's kind of related to my research, I might propose us to do that first. It's Acer, or basically actor critic with experience replay. As we, experimented, as it's been shown in our experiments, algorithm with experience replay always have better sample efficiency. They always learn so much faster given the same number of time steps. And I think it might be interesting to look into how do you incorporate the experience replay with policy gradient methods. And to show you kind of the results that they have, this is kind of a comparison between the red line is the algorithm of the paper, and A3C is just this actor critic. And given the same number of time steps, the using a replay buffer is obviously significantly faster.
Yeah, looks good.
Yeah. All right. Mm, yeah. But yeah, definitely something interesting to look into. I'll probably, um, yeah, yeah. Well, yeah, I think if everyone's okay with it, let's probably try to implement the Acer or read about it next week or the week after. Um, but yeah.
Actually, I've started to read that paper and
Oh, really?
quite some heavy theory behind
Yeah.
all
So
those
yeah, there.
residual TD, that kind of stuff.
Beg your pardon.
Especially that retrace algorithm as well as the residual TD they're using.
Yeah, I feel like the paper might be more difficult than the actual implementation. So, for those of you who don't know, Minimal RL is always the library that I always, seek intuitions from. They have very simple implementation, very easy to read, and this is it for their Acer implementation. I think something that they didn't implement was there's this concept of trust region enforcement in the Acer paper, and I think in this paper they don't really do that part. But everything else, I think they do, and it doesn't seem that complicated, right? Yeah, it just seems a lot more accessible. But we'll see once we start to mess around with it. And I don't know, for the off policy gradient, it feels very confusing sometimes. Um, I was discussing this with my advisor today, actually, and I don't know if I have it. I was reading something about the off policy gradient, and it kind of looked like this, like where is the policy gradient comes from. So this is the proof that I find very intuitive and kind of convincing at the same time. So imagine you're maximizing the advantage estimator or a Q estimator, which is your Q function. If you can maximize the Q function, then so the Q function is, of course, following a particular policy. So if you can maximize the value of the Q function, since it's following the policy, then you have the policy gradient. So your objective always looks something like this. And how do you derive the policy gradient is, first of all, you expand the expectation formula, which gives you the summation over all possible actions times the probability of executing a particular action times the advantage. And then its gradient, basically, you take the gradient with respect to theta, and then you take the gradient of the probability with respect to theta, and then you still multiply by the advantage estimator. And then the trick, what they call, is to multiply by 1, which is you multiply by pi over pi, which gives you 1. However, once you move the pi on the top to over here, then this part can be replaced by the expectation, can be unexpanded into the expectation formula again. And then you're just left with the right part. And then another thing is you can combine this d pi d theta over pi to become log the d of log pi over d theta. If you think about it, it's an identity because the derivative of log is equal to 1 over uh, 1 over x times whatever is inside. So this essentially expands to 1 over pi times the derivative of inside, which is this term right here. And then that's how you got the policy gradient, the standard log probability form. And then I was reading this proof on Reddit, which, may be untrue, but it seems rather convincing. And I was trying to read how is TRPO different from the policy gradient? Why does the log probability just kind of disappears? And it's a very convincing argument. Still, you expand the expectation, replace it with the summation of all possible action times the probability of executing those actions. So in our case, it's pi times the advantage estimator. And then the trick is also multiply that by 1 over 1. And then you have the b, the probability of executing A following policy behavior. And then because of this term right here, and then you can unexpand it into the expectation, and then you're just left with basically the objective in the TRPO paper, which is the importance sampling times the advantage. However, when I was reading some difficult theories, I don't know, it's really hard to read. This guy, Lil's log, he wrote a very good overview.
She wrote.
Beg your pardon?
She wrote.
Oh, she wrote it. Oh, I didn't know.
Very brilliant. She works at OpenAI, I think, on the robotics team.
Oh, okay. My bad. So she wrote this excellent piece on a survey on all of the major policy gradient methods, and his derivation on the off-policy gradient becomes different. See here, she still has the expectation of action sample from beta, but somehow the log probability is remained here for some reason, and it's I can't think of any reason why is there. It has a really weird part over here as well. Ignore the red part. Yeah, I don't know.
I always thought the logarithm was used for numerical stability.
No, it's not. It's the derivation.
I see.
Yeah, so if you look at the derivation over here.
Because there is a 1 over something.
Yes.
Okay.
That's the moral of the story, because you have this part and this part, and these two parts becomes a logarithm. So this thing can be also found in the Rich and Sutton's book, but unfortunately in the Richard Sutton's book, he doesn't talk about the off-policy gradient that much. He did talk about importance sampling, but not in the policy gradient section, and I am a little bit disappointed because of that. So if you read the paper about that part, here is a policy gradient, and essentially it becomes something like this, and then you can change this to something like the logarithm. And the way you do it is you multiply by 1, right? And this is 1. And then this part, yeah, he has some notations. It's like changing from the samples of the random variable to random variable itself. But then it goes over here, replaces this term with an AT, and then you just have this part. And then this part is the log. Whoa, where is it? But this part is essentially the log of probability because of the identity. Um, the derivative of ln x is equal to the derivative of x over x. So that's this part. But yeah, always so many things that are difficult to understand, but hopefully hopefully these will be beneficial to creating better algorithms, doing better research, things like that. All right. Any questions or comments? And I just noticed, Niju just joined us. Did you try out with the implementation by any chance? Maybe his mic wasn't working. But yeah, anyone else have any questions or comments? If not, I would thank everyone for joining the discussion. I'm very happy that we have a state-of-the-art algorithm working, achieve very good results. And either for this week or next week, either for next week, I'll have to decide whether to sort of stay with TD3 or do something else, like make the code format looks more consistent, or but if I don't decide to do those things, then we should go ahead with the Acer paper just to see how experience replay could be applied to policy gradient methods.
Sounds good.
Yeah, cool.
All right, great. Thanks everyone for coming. Have a great weekend and stay safe.
Yeah, thank you. Bye-bye.
All right, bye. Have a good one.
Bye.
I'll also stop the recording.